Hi, so in this section we're going to look at some examples of log and exponential functions where we're using u substitution. So our first example is the integral of e to the 4x dx, and our job is to evaluate this integral. In other words, find the antiderivative of e to the 4x dx. Now, the two things that I know that the antiderivative of e to the x is e to the x plus c, and I know that the antiderivative of 1 over x dx is natural log of the absolute value of x plus c. So these are the two new pieces of information that I have. When I look at this integral, I see e raised to stuff, but the thing is that that exponent is more complicated or fancier than just an x. And so when I see fancy stuff inside parentheses or maybe up in a power, when I see that fancy stuff where it's fancier than just a plain x, I want to think about doing a u substitution. And when I have an exponential function, my choice for the u is often going to be the stuff in the power, and that stuff is often fancy. So we choose the fancy stuff that's in the power of the exponential function. So our choice for u will be 4x. All right, now when we do a u substitution, after we choose the u, we continue to do some work off to the side. So our choice of u is 4x, and we take the derivative, and the derivative of u is du over dx, and the derivative of 4x is 4. Once I take the derivative, now I want to solve for dx. So I can multiply both sides by dx, and I have du equals 4 dx, and then I can divide both sides by 4, and so what I have is that dx is equal to du over 4. Okay, so all of this work off to the side, the two pieces of information that I want to hold on to are that I chose u to be 4x, and that I solved and found that dx is equal to du over 4. Once I have those pieces, I can go back to my original integral over here and make some substitutions. So I still have this long stretched out s. I replace the 4x with u, that was my u value, so I have e to the u, and I replace the dx with what I found dx to be equal to. So I replace dx with du over 4. Okay, so now I look at this integral. A lot of times in u substitutions, after you make those substitutions, you still have a mix of u's and x's. In this case, we don't have any x's left over, so that's good, but we still have a little bit of cleanup to do. And the cleanup that I want to do is this 4 that's under the du, I want to push that number to the front. And so I have the integral. When I write down the 4 was in the denominator, and so when I push it to the front, I need it to stay in the denominator, so I need a placeholder of a 1 in the numerator. So I have 1/4 e to the u du. Okay, I've transformed this integral entirely into the variable of u. We've done a u substitution. I've cleaned it up. Now I'm ready to find the antiderivative. So my antiderivative of 1/4 e to the u, now that's not fancy up there, that's just one letter. So the antiderivative of e to the u is e to the u. And if I have a number sitting in the front, I carry it along. So I have 1/4 e to the u plus c. It looks like I did absolutely nothing there except for erase the integral sign, but what I just did from this step down to our next one is find an antiderivative. Okay, so we found our antiderivative, and when we do a u substitution, our last step is to replace the u back into whatever it was at the very beginning. And so our u is 4x, so our final answer is 1/4 e to the 4x plus c. And if you want to, you can take the derivative of this, and it should give you back e to the 4x. And you can check that if you want to. Okay, let's look at another example. In our next example, we have the integral of 1 over 3x minus 2 dx. All right, looking at this fraction here in the middle, what I see is there's an x in the denominator, but it's not raised to any powers. But if I group everything together down there, it's fancier than just an x. So I'm going to do a u substitution on this problem because that denominator is fancier than just an x, and the x is not raised to any power. So we start by choosing u. And our choice for u will be the entire denominator, 3x minus 2. Okay, once I make my choice for u, I keep working off to the side. I take the derivative of u, which is du over dx. And I take the derivative of 3x minus 2, which is 3. Okay, once I take the derivative, now I solve this equation for dx. dx is in the denominator, so I need to multiply both sides by dx. So I have du is equal to 3 dx, and I can divide both sides by 3. And that will leave me with dx is equal to du over 3. And that's important, so I'm going to circle it. Okay. So now I go back over to my integral and I make my substitutions. So one substitution I make is that this 3x minus 2 is our u value, so I have 1 over u, and my dx, that's equal to du over 3. Okay, so I look at this and I ask myself, do I have any x's left over? And the answer is nope. So I'm happy about that, but it's not completely cleaned up because I have this 3 sitting under the du. I'm going to push that 3 to the front right next to long stretched out s. And because that 3 was in the basement, the 3 has to stay in the basement, so this becomes a 1/3. So I have 1/3 times 1 over u du. All right, now I'm ready to take an antiderivative. Okay, so I look at what I have. I've got a number times 1 over u, and 1 over u is kind of like 1 over x, except for the variable is u. So my antiderivative will be, I'll carry along the number, 1/3. The antiderivative of 1 over u will be natural log of the absolute value of u, and then I have a plus c at the end. Okay, so we took the antiderivative. Our last step in our u substitution is to replace the u with 3x minus 2. So we have 1/3 times the natural log of 3x minus 2. I put absolute value bars around that because of that technical issue with the domain. And then I have a plus c at the end. So here is our antiderivative. Okay. I'm going to do 2 more examples. I would encourage you on these problems, as well as the problems from section 12.2, when we first started to talk about u substitution, I would highly, highly encourage you to take a look at the practice problems for these sections. These u substitution problems feel really big. Like, there's a lot of steps to them. And when you're seeing the steps for the first time, it can feel like a lot. But the more you do of these, the better they feel and the more they kind of click. So keep working on these. If you're feeling a little overwhelmed by these u substitution problems, keep working on them. Stop by my office hours in Zoom, email Ryan, talk to Ryan about them, hang out with Ryan and work on a bunch of these problems. The tools that we're doing right now are going to be used in our next chapter because we're going to be dealing with antiderivatives and we're going to want to have interesting and more complicated functions. So we're learning the tools now so we can apply them later. All right, in this example, we have the integral of 5x squared over 3x to the third minus 8. And so we have a lot of stuff going on. We have a fraction, and there's a function on the top and a function on the bottom. Typically with a u substitution, if you have something fancy, you choose the inside function. Now here, there's no sort of hugging of powers going on, but sort of a secondary rule of thumb for choosing the u is to choose, if you have a fraction, to choose the denominator. And so for our choice for u, we are going to choose u to be 3x to the third minus 8. Okay. All right, so my work on the side, I'm going to take the derivative. So my derivative of u is du over dx. My derivative of 3x to the third, I bring the 3 down, so I have 9x squared minus 0. And now I want to solve for dx. So I can multiply both sides by dx. I have du equals 9x squared dx. Now I can divide both sides by 9x squared. And so on the right side, I'm left with dx, and on the left side, I'm left with du over 9x squared. Okay, so the important pieces on my side work are my choice for u and the value I came up with when I solved for dx. Okay, so back to my integral. I have the integral of 5x squared. I'm going to substitute u in for 3x to the third minus 8, so I have 5x squared over u. And my dx, I'm going to replace with what I solved for dx. So my dx is equal to du over 9x squared, so that's what I'll write down here instead of dx. Okay, so now I look at everything that I have here, and I have a mix of u's and x's, which means that I'm not quite ready to take an antiderivative. I have to make sure that everything I have is entirely in terms of u. Now, as I try and cancel things, I'm happy because I have an x squared on the top and an x squared on the bottom, and they cancel, which gets rid of all of my x's. If I did not get rid of all of the x's, something went wrong. And the things that could go wrong are, maybe you made a bad choice for u, or maybe you made a mistake in your derivative, or maybe you didn't quite see how to cancel things over here. So those are 3 possibilities, or maybe it's just not a good u substitution problem. But the idea is, based on your choice for u, you want to make sure that all of your x's cancel. Okay, so now we have the x's canceled. To clean this up, I'm going to push all the numbers to the front. So we have the integral of, I have a 5 on the top and the 9 on the bottom, so I have 5/9 times, now I have this u, but the u is in the denominator. I need something above it, so I have a placeholder of 1. And then I have a du at the end. Okay, everything's cleaned up, and now I'm ready to find my antiderivative. So I take the antiderivative, and while our original function was incredibly complicated, now what I have is a number times 1 over u, and I look at 1 over u and I say, boom, the antiderivative of 1 over u is natural log of u. So we have 5/9 times the natural log of the absolute value of u plus c. Okay, we've done the calculus. The very last step is to replace the u. So we have, as a final answer, 5/9 times the natural log of, and our u is 3x to the third minus 8. I'm glad I circled that. So natural log of 3x to the third minus 8 plus c. And this is my final answer. The derivative of the thing inside the box is this fraction up above. Okay, so we have one final example that I'd like to look at today. And in this example, we're going to look at the integral of x e to the x squared dx. All right, so there's a couple of things going on here. I have some multiplication between the x times e to the x squared. And the other thing that I have is that this exponent, the power up here, the x squared, is fancier than just an x. So because there's multiplication of functions going on and there's fancy stuff up in the power, this is a good candidate for a u substitution. So I'm going to choose a value for u. And the choice I'm going to make, because I have an exponential function, the choice I'm going to make for my u is going to be my power on the exponential function. So in this case, our u is going to be x squared. I'm going to circle that because it's important and we'll need it. Okay, so now I want to take the derivative. The derivative of u is du over dx. The derivative of x squared is 2x. Once I take this derivative, I want to solve for dx. Now, after you've done about 50 or 100 of these problems, this part about solving for dx is you're going to see some patterns going on. And those patterns work every time. So I multiply both sides by dx. So we have du equals 2x times dx. Divide both sides by that 2x. And we have that dx is equal to du over 2x. So the pattern here is that once you take your derivative, then your dx is always going to be equal to du divided by the derivative of the u. And so if you want to, you can skip these intermediate steps. I like to write them down every time, but I know not everyone likes to do that. Okay, so these are the parts we have. We want to go back to the original integral and we want to make some substitutions. So the substitutions that I'll make, I'll replace this x squared with u, so I have x times e to the u. And I'm going to replace the dx with du over 2x. Now, if life is good, then all of the x's will cancel, and they do. I've got an x on the top and an x on the bottom, and so those cancel. And this 2 that's below the du, I'm going to clean this up by pushing that 2 to the front. So that 2 was in the denominator, so I want it to stay there. So I write this as 1/2 e to the u du. Okay, so everything has been cleaned up now, and now I'm ready to take my antiderivative. Okay, so my antiderivative, I have a number times e to the u, so I'm going to carry along the number, 1/2. Take the antiderivative of e to the u. Now, antiderivative of e to the u is e to the u. It looks like I didn't do anything here, but I actually did. I took an antiderivative. And then I have a plus c. Okay, so I've taken the antiderivative, and my final step, I want to answer my final answer in terms of x's because that's how the problem started. So I'm going to substitute back in my u was x squared. So I have 1/2 e to the x squared plus c. And this is our final answer. And you can check that if you take the derivative of what's inside the box, you should get back x times e to the x squared. Okay, so again, there are practice problems listed for this is section 12.3, and also in 12.2 on use substitution. And I highly encourage you to stop by office hours and work on them with me, or stop by Ryan's office hours, Zoom office hours for both of us, but stop by and work on some of these problems, or write out some of the practice problems and you can send them to me in an email and I'll give you feedback on them. But definitely get good at working with these antiderivatives. Okay, thanks for listening. Have a good night.